Over to you, ma'am. You can share the.
Thank you so much. Wish you all a very good evening. And first of all, let me thank Professor Nanda for inviting me and portraying such a big picture of me. Thank you so much, Professor Nanda. Um, so my area of research is nature-inspired optimization techniques. And let me just share my screen and let me know if you can see my screen. Just a minute. Mm. Screen. Oh, where is that?
Ma'am, here at the bottom,
Yeah. But
there is a sharing of.
no, share to I got it.
Uh,
It is just a minute. Yeah. Can you now see it? Can you
yes,
see my
yes,
PPT?
yes, yes, yes.
Oh, yeah. Okay, great. That's just great. Okay. Right. So, again, it has gone.
Ma'am, just change. Yeah, now it is gone.
Is it? It's gone now, huh?
It's gone now.
Just a minute. Screen. Give me a minute. Yeah. Now it should be visible.
Yes,
Visible now?
yes, it is visible, ma'am. Just change the slide.
Yeah. I will be changing the slides. Okay.
Yes, yes, yes.
Right. So my area of research is nature-inspired optimization techniques, and as Professor Nanda mentioned, uh, my uh, initial work on nature-inspired techniques was on genetic algorithms, and that is why genetic algorithms is very close to my heart. So I will be quickly going through what exactly genetic algorithms is, and I will be sharing with you some of the main operators of genetic algorithms, how they are working, and how does it affect the solution. So, a brief introduction about genetic algorithms is that the father of genetics algorithm is Professor Howland. So, Professor Holland was very active in the year 1975, and he and his team of students worked on this. Genetic algorithms are those algorithms which derive their inspiration from living organisms. Today, many people are working in this area, and of course, my contribution was particularly um, unknown caller. My my contribution was particularly effective in the year 2007 when one of my students proposed a real coded genetic algorithm. Uh, those of you who are interested in working in this area, I would recommend these books. Of course, there are many. I mean, there are hundreds of books, but I feel these books are one of the uh, simplest way of understanding the genetic algorithms. Uh, if you want to look at Python, then you can study these books. Of course, this FDP is on MATLAB, so I will not comment on that. Of course, Python and MATLAB, both of them are uh, equally good to solve your problem with the help of GA. So let's look at what is the basis of Darwin's theory of evolution. Now, the genetic algorithms is based on the Darwin's theory of evolution, which states two principles. One is the principle of inheritance, and the other is the principle of competition. Now, inheritance means that all living organisms, they pass on their good traits from the kth generation to the k plus 1th generation, which means, for example, let's say in human beings, we want that our next generation, that is our children, are either beautiful as we are, or they are smart as we are, or they are intelligent as we are. So the good features should be carried over to the next generation. That is what is called as inheritance. And in terms of optimization, we can say that those solutions which are good, that is good with respect to some criteria, which we will define very soon, we should expect that those good solutions should pass on to the next generation. And the second principle is the competition, that is the survival of the fittest, which means that depending upon a criteria which we call as the fitness criteria, we expect that only those individuals should survive which are fit, and the rest of them should die. And therefore, there is a competition between each and every individual. So the genetic algorithms mimics the life on the earth, and as you know that on this earth, the life began with the help of one single cell amoeba, and slowly and slowly, these living organisms, they developed more and more complicated creatures, and after millions and millions of years, we came up to the situation of human beings, and maybe after some more couple of years, we will end up into superhuman beings. Now, this situation did not happen in 1 year. This went on and on for multiple years, and this kind of a phenomena, we will be looking at the way in which this phenomena is implemented in the case of genetic algorithms. So first of all, let us look at one cycle of the genetic algorithm. Now, this slide tries to depict uh, what happens in the initial stage. Uh, before I proceed, I hope everybody is familiar with the fact that in the case of nature-inspired techniques, we are talking about multiple randomly generated feasible solutions, and those randomly feasible solutions are updated iteration after iteration. So that is the characteristics of all nature-inspired optimization techniques, vis-a-vis the point-to-point methods, like for example the Newton's method, the Newton-Raphson method. We start from an initial guess, keep on updating that initial guess with a hope that that initial guess will reach the minima. But this doesn't happen here in the case of genetic algorithms, and for that matter, all nature-inspired optimization techniques. In the case of genetic algorithms, we generate a randomly generated set of feasible solutions and update this randomly generated feasible solution set over and over in various iterations. Now, in this diagram, I am trying to depict what happens in one particular cycle. Here, you will see that amongst these randomly generated feasible solutions, by the way, which is called as population. So, from this population, uh, all the individuals are evaluated by using a fitness criteria, and the ones that are the fittest, they are selected and placed in the mating pool. So here is the you know the property of Darwin's theory of evolution, that is, the fittest, they are going to be carried over to the next generation, whereas the others are going to die. So therefore, the fittest one are selected and placed in the mating pool, and from this mating pool, another operator which is called as the crossover operator, that is implemented. That is, this crossover operator is similar to the breeding that is found in all living organisms, which means that the good traits of the parents are passed on to the next generation, that is the children. So this operator, crossover operator, is implemented, and after this, these children are passed through another operator which is called as mutation, and the objective of mutation is to bring diversity into the population, and a small change is made in these chromosomes, these individuals, and then this cycle is completed. So it means that the one cycle of a GA consists of all these operations. We will study how these operations work in various scenarios. So once we have understood one cycle, now let us look at the entire algorithm. So the flow chart of the genetic algorithm looks something like this. That is, initially generate a random sample of feasible solutions, which is called as the population, and evaluate each of them using the fitness criteria. Then, based on the crossover and the mutation operator, um, keep on moving into the next generation. And whenever the stopping criteria is satisfied, that is the place we have to stop. Otherwise, the iterations are carried over further and further. Now, there is a whole lot of a biological background based on which the genetic algorithms are based upon. So we all know what is a cell and how chromosomes are defined. I think I can skip this because we have to complete this within the uh, stipulated time. What I'm trying to say is that the genetic algorithms are uh, implemented using the Darwin's theory of evolution, which is applicable to all living organisms. So, what is the advantages of GA? The GAs are very adaptive and they learn from their experience. Now, what does this mean? This means that for different scenarios of problems, uh, we can define a new genetic algorithm. By this, I mean that if the problem is of a binary nature, then we can define a binary genetic algorithm. If the problem is of a real coded nature, then we can define a real coded genetic algorithm. And similarly, the permutation or hexadecimal and so on, and in fact the tree also. So depending upon the problem, you can define a new GA. And this is what is the meaning of adaptive. Usually they learn from their experience, means that whatever has happened at the kth generation is going to affect the next generation. Therefore, since you see, because what is our objective? Our objective is to solve real life problems, and in reality the problems that arise, they may be of tremendous variety. They, as I said, they may be binary, real, octal or hexadecimal, or tree encoding. So therefore, depending upon the real life problem, we can design a new GA to our convenience. uh, and that is the reason why it is said they can be very efficient in solving complicated problems, because of the flexibility that is available. And let us say, as a programmer, you can design a new genetic algorithm the way you like, depending upon your problem at hand. All right. So, first of all, let us try to understand the basic difference between the genetic algorithms and the traditional algorithms. So, as I said, that the GAs, they work with a coding of parameters, not the parameters themselves, which means that you can solve a real life problem, let's say a real valued problem, with the help of binary GA, and vice versa. So instead of the decision variables, you can you can actually solve it with the kind of genetic algorithm that you want to use. For example, you can use binary genetic algorithms to solve a real valued function. Secondly, the genetic algorithms, they search from a population of solutions instead of a single solution. So, just as I mentioned, that a single solution means that starting from an initial guess, you keep on updating that solution. This doesn't happen in genetic algorithms. In genetic algorithms, usually we we generate a population and keep on updating that population. The third difference is that the genetic algorithms, they use the objective function information, which is also called the payoff, and instead of the derivatives. You must have observed that when we are defining nature-inspired optimization techniques, we do not make use of derivatives and other auxiliary information of the objective function or the constraints. And in fact, the GAs, they use the probabilistic transition rules instead of the deterministic rules, which means that the transition rules, for example, the crossover and the mutation, etc., they are based on the generation of random numbers, and the you see By saying that generation of random numbers, I mean that instead of a set transition rules, it has probabilistic transition rules. And more and more random numbers are available, the better the result is expected to be. So here are the main operators of the genetic algorithm. The first one is called encoding, which is a one-time operator. And I said encoding, just as I mentioned, it could be of binary, hexadecimal, real, and so on. The remaining operators, that is selection, crossover, mutation, and elitism, they are those operators which are applied repetitively, one after the other, till the stopping criteria is satisfied. Now, here comes some of the common terminologies. First of all is the population. So, population is a collection of several alternative feasible solutions of the given problem. Just as I mentioned, the initially randomly generated feasible solutions. Uh, each individual in that population is called as a chromosome, and the individual character or the symbol in that chromosome is called the gene. Now, the population size means the number of individuals or the number of chromosomes. And as I mentioned, that every individual has to be evaluated based on some function. So, the fitness function can be defined as an evaluation function so as to determine the fitness, how fit each and every individual is. So, usually it's a user defined and depending upon the problem at hand. So, this is called as the fitness function. Then we also have to define the value of the fitness function evaluated at each of the chromosomes. That is what is called as the fitness. So first of all, let us look at the first operator, which is the encoding. As I mentioned, the encoding is a one-time operator. Here it is. It's a one-time operator. This tells us which kind of parameters we want to use. So this is what I mean by saying encoding. In general, encoding could be of many types, as I mentioned: binary, real, permutation, tree, and so on. Um, let's take the simplest case of binary. Now, the binary encoding means that every chromosome is a string of bits, either of 0 or 1. So, the chromosomes could be of something of this kind, right? That is, there could be a collection of, let's say, 8 bits of 0 and 1. Why only 8 I have chosen? This is just an example. It could be 10, it could be 100, I mean, it could be any other number. And in fact, we'll see what it means. Now, since uh, our design variables are given to be something else, let's say real, okay? Now, instead of the real numbers, we want to use the binary numbers. So what we do is we try to determine a mapping from the design variables to the binary numbers. So this is the way the binary map, the mapping has to be defined from the design variables to the binary numbers. Now, in order to define this, here is a simple example. Suppose I want to use 4-bit binary strings to encode 16 positive numbers. So I starting from 0, I start with 4-bit encoding, that is 0000. That is the numeric value is 0. Then 0001 is 1. And as you can see, what is this mapping? This is the normal way in which how you can encode the positive integers from 0 to 15. So there are 16 of them, okay? And I can say that the 4-bit encoding can be used using this mapping. In this case, you can see this mapping has been created with the help of how every binary equivalent of any number can be obtained. For example, the binary equivalent of 9 is 1001. So I think you all know how to do it. Similarly, the reverse can also be obtained. 1001 can be written as binary format like this. And now, what happens? Suppose there are two variables. Till now, we were just talking about one variable. Suppose now we have two variables. Then how we are going to look at the scenario? So, the two variables can be represented like this. So the first 10011 that I've written, this is corresponding to the first variable x1, and similarly the second part, that is 0110, this is corresponding to the second variable. Purposely I have left a small space in between, uh, just for our understanding, although in general uh, this space does not really have any meaning, but we are keeping it, we are just separating these two quantities so that we can understand, for our understanding. So the 4-bit string can represent integers from 0 to 15 like this. That is the lower limit, and the upper limit of the binary encoding can be mapped to the lower limit and the upper limit of the um, given problem. And like this, the n-bit string can represent integers from 0 to 2 to the power n minus 1. Now, if xi is coded as a substring si of length ni, then the decoded value of a binary substring si can be written by using this formula that I mentioned earlier, 2 to the summation of 2 to the power k times sk, where si can be either 0 or 1, and the string s can be represented as follows. So the reverse order, it can be written like this. As an example, suppose we want to understand how this mapping works. 4-bit string, let us say 0111, has a decoded value as follows using the formula that I mentioned. Okay, that's the formula. And I have now converted uh, this into 7. Therefore, for known lower and upper bounds corresponding to the lower and upper bound of the binary, the equivalent value for any 4-bit string can be obtained using this formula. That is, xi is equal to xil plus xiu minus xil upon 2 to the power si minus 1 multiplied by the decoded value of the string. And like this, once the encoding has been defined, we can use this formula to match any variable within that lower and upper bound into the lower and upper bound of the binary. And similarly, vice versa, also we can do that. If suppose you know the lower and upper bounds of the real, for example, the lower is 2 and upper is 7, and we want to find out what value of 4-bit string of xi would xi equal to 1010 that would represent. So what you do is, first of all, you find out the decoded value of si. 1010 is nothing but 10 if you use the expansion, and xi is going to be 12 using this formula as I mentioned over here, right? And that is how you can get an accuracy obtained as 1 upon 16th of the search space. Why is it 16th, 1 upon 16th? Because 2 to the power 4. So 2 to the power 4 is, uh, 16. Now, if the string length is increased, let's say to 5, then the obtained accuracy will be 1 upon 32th of the search space. And therefore, you can keep on increasing the accuracy by increasing the number of bits. Here we have used 4 bits. If you use 5 bits, you get better and better approximation. And like this, all variables need not be of the same substring length. One of them could be 1 and the other could be other. Okay, similarly, the octal encoding works, and also the hexadecimal encoding on the same lines. Only thing is, we can use the 4-bit octal or the 4-bit hexadecimal encoding. Other encoding is the permutation encoding, which means that from one node to another node, the traversal is defined, and the population can consist of like this. So chromosome A, chromosome B, and so on. Usually, these kind of encoding is required in ordering problems, particularly the NP-hard problem, traveling salesman problem. You know what is NP-hard? NP-hard problems are those problems whose complexity keeps on increasing as the size of the input increases. Apart from this, we also have what is called as the value encoding. Usually, it is used in optimizing the weights of the neural networks from the hidden to the output layer. So the question is, what do you mean by population size? The size means how many chromosomes should be generated in the population. Usually, there should be a proper balance between the small and the large size because of its various advantages and disadvantages. And the way to initialize a population is either loaded from the secondary storage or randomly generate them. Next comes evaluating of the objective function or evaluating the chromosome. In general, in genetic algorithms, we say that a collection of rules which specify which conditions on an individual have to meet for a good solution. So, as I said, the fit ones are going to survive, the rest of them are going to die. And the good ones have to be maximized. So, that's why maximize the fitness. In general, when we have a maximization problem, then the objective function and the fitness is the same thing. So if you do not, if you use this notation, capital Fx as fitness and small fx as objective function, then for the maximization they are same. Whereas in the case of minimization, you can define it like this: capital Fx is equal to 1 upon small fx, or you can say equal to 1 upon 1 plus fx if fx is equal to 0. So you can define it the way you like. And in fact, this can also be user defined depending upon the problem at hand. So the next operator is the selection operator. The selection operator tells us that preference has to be given to the better individuals so that they can be allowed to pass on to their genes to the next generation. And the goodness of each individual is going to depend upon the fitness. And the fitness, as you have seen, may depend upon some kind of a objective function or some kind of a subjective judgment. Now, there are again numerous kinds of operators, selection operators that are available. The common ones are the tournament and the roulette wheel. And of course, there are others also. So the tournament selection is the way in which, when we observe the cricket matches, so a tournament is played between a pair of individuals and the best one is placed in the mating pool. Similarly, over here, the best one is placed in the mating pool, and like this. So the tournament is played between every pair and it is placed into the mating pool. Now you will find here the size of the population has decreased because earlier there were 8 individuals. Now there are 4 individuals in the mating pool, but we can take care of that. How can we take care of it? Here you see, suppose we have a objective function like this. It's a two variable function, and we have the strings from 1 to 8 and their fitness. So the last column shows their fitness. So what we're going to do is we are going to play a tournament between uh, the second string and the fourth string. So what do we find? What is the second string? Second string has fitness 2.1 and the fourth string has fitness 4.01. Which one of them is winner? Winner is 4 because 4 is having a higher fitness. Remember, objective function is the same as fitness because in this case, our objective function is of the maximization type. And like this, we can keep on repeating this procedure by playing a tournament between 2 and 4, 3 and 8, 1 and 3. Now, the question is, you will say, why only 2 and 4? Why only 3 and 8? The answer to this is this choice is done randomly. So randomly, the ith and the jth individuals or the chromosomes have been selected, and whosoever is the winner is going to be placed in the mating pool. So this is the mating pool. Now, what do you find? Once you have completed this kind of an operator, you find that the chromosome 1 and 7 are not selected. And what is the reason why they are not selected? Because 1 and 7 are having low fitness. 1 is having fitness 1 and 7 is having fitness 1.93. You might note that the sixth individual is also having low fitness, 1.91. But never mind, that is the properties of genetic algorithms. It might be changed in the next iteration. So therefore, we find that 1 and 7 are not selected because they are having low fitness. On the other hand, 4 and 8 are selected twice. As you can see in the second column, 4 and 8 have been selected twice, and the others have been selected once. So this is the mating pool. Mind you, this is only one iteration. This procedure is going to be repeated in every iteration. So probably things are going to be settled out. And this is what the new population looks like after the tournament selection has been applied. There's another very common selection operator which is called as the Rowlett-Wheels selection. It is based on the entire behavior of all the individuals. I can skip this because we need to move further. So here I have given a small exercise which says that minimize x1 squared plus x2 squared subject to this domain. So what I would like you to do is generate the initial population of size 20 and use the tournament selection and the roulette wheel selection to obtain the mating pool. And also it would be interesting to plot the initial population and the mating pool using both the methods. Next comes the crossover operator. As I said, crossover operators are also of multiple types, and they also depend upon the way in which the encoding has been done. So the single point crossover can be defined like this, which is very simple. Here you have two chromosomes, chromosome 1 and 2, and randomly a crossover site is generated, in this case the fifth site. So the fifth bit has been selected as the crossover site, and you find that from the two original chromosomes we generate two new offsprings in such a manner that from the fifth bit onwards the trailing bits are swapped, and the color coding tells us how this is working. Note that there is a small gap in between to indicate that this may be a two variable problem. Okay, so this is the first variable and this is the second variable. So the chromosome should be consisting of all the variables in the problem. So if you have a 10 variable problem, then the 10 variable should be represented like this. Like this, there are other crossover operators also, the single point operator, the double point operator, which means that the in between the two sides, the bits are swapped. And there is also one operator called cut and splice, where you have two different sites. So each chromosome is having a different site of its own, and the trailing bits are swapped. It is interesting to note that the length of the chromosome is going to change, but doesn't matter. That's the way this operator is defined for various kinds of problems. Similarly, there is a uniform crossover. Now, after applying any of these crossovers, I mean, it's not necessary that you have to apply all of them. You are free to choose the operator that you like, depending upon the problem at hand. Now, the next question arises, how many chromosomes should participate in the crossover operator? And the answer to this lies in the definition of the probability of crossover. Now, this PC is a real number defined between 0 and 1, which decides the percentage of chromosomes which should participate in the crossover operator. For example, if the PC is 0.25, then 25% of the chromosomes should participate in the crossover operator. So it is not necessary that all the individuals or all the chromosomes should participate in the crossover operator. Only how many will participate is defined with the help of the probability of crossover. So you can write a small procedure. Uh, if the probability of crossover is 0.25, then for the entire population, while k is less than pop size, generate rk, where rk is a random number between 0 and 1. If this random number is less than 0.25, then select this chromosome as one of the parents for the crossover, and increment this k, else move further. So like this, with the help of this simple procedure, you can decide uh, which chromosomes should participate in the crossover operator. So here I've taken a small example. This is a small problem where you want to find out the values of A and B. Twice A squared plus B is equal to 57. We can model this problem as a minimization problem of uh, minimize f of AB equal to absolute value of 2A squared plus B minus 57. And I have generated a population. So A and B are generated randomly. Here you can see they are the positive integers, and I've calculated their f. So what is f? F is this absolute value of 2A squared plus B minus 57. Capital F is the fitness, because this is a minimization problem. So I would like to make capital F equal to 1 upon small f. So that is the that is the fitness. And then okay, I've used the roulette wheel here for the selection. But anyway, you can just look at it, it's there. So after the selection, this is the population that I get after the roulette wheel selection. Now, coming to the crossover probability, let's say 0.75, I can use uh, this crossover probability 0.75 and determine the mating pool. So that is the mating pool. So corresponding to every individual, 0.2, I'll compare it with 0.75. Since it is less, so I need the mating pool. I'll generate the mating pool, and like this for the others. Observe that the second case and the last case are left blank, because the probability, the random number that we have generated is 0.9 over here and 0.8 over here, which is bigger than 0.75. So therefore, no crossover is to be implied, and that's why these two rows are left as blank. After that, the crossover is obtained like this, and you can see the uh, what is the behavior of the fitness, the objective function and the fitness. You can see that now it has become 19. Earlier it was 22. So the best one was 22, because small f is a minimization. Here also we are seeing that it is now improved from 22 to 19. And remember, this is only just one iteration. Things might improve when we apply more and more iterations. Then another example, which is a different kind of an example, that the chromosomes are consisting of ones and zeros, and the user is supposed to define the fitness depending upon the number of ones that are appearing. So here you find the fitness is 4 because there are 4 ones over here. Here the fitness is 3 because there are 3 ones over here, and like this. Now I'm going to generate a random number in this column and use a tournament selection. So I play a tournament between 1 and 2, and the random site is 5, and that's how it gives me 2 more chromosomes and their corresponding fitness. And what do we find? That once this is implemented, the last column tells us that the third individual and the ninth individual are giving us the best fitness. Okay, here's another problem. It's called the traveling salesman problem, which uses the permutation encoding. So let me just skip this so that we can move on to the mutation operator. Now, what is mutation operator? Mutation operator is a specialized kind of an operator which is very, very important in every genetic algorithm. And why is it important? Because look at this example. Suppose there are 4 chromosomes in the population as shown over here, and each of the chromosomes is having a 0 at the first place over here. You can see it's having 0 over here. Suppose The minima of this problem had 1 at the first bit. Suppose the minima of this problem had 1 at the first bit, then no matter what crossover you use, you will never reach the minimum. So therefore, you need to design another operator which can take care of it. And that is the way the mutation is defined. In order to understand the mutation, let's look at what do we mean by Hamming distance. Here we define the Hamming distance between two strings of equal length as the number of positions at which the corresponding symbols are different. For example, 101, 1001, and you find that only at the fourth bit uh, there is a difference, whereas the others are same. Therefore, the Hamming distance is 1. And you can see that in this case, suppose we generate a new chromosome with a small Hamming distance, hoping that there will be 1 at the first bit, we are likely to reach the optimum. So, what are the advantages of the mutation operator? This helps to escape the genetic algorithm from the local minima. You know, there are local and global minimas, and therefore, uh, in order that the genetic algorithm may not get stuck in a local minima, this kind of an operator where we can play with 1 bit at a time is going to be useful in escaping the local minima. Also, it provides some kind of a diversity in the entire population, and that's why mutation is required. Now, again, there could be numerous types of mutations. Some of them I've listed over here, and I can illustrate what do we mean by a single point mutation. In this case, suppose we have an original string over here like this. We need to generate a randomly generated mutation site. So, for example, the fourth one is the randomly generated mutation site. And what we'll do is we'll observe it. If it is a 1, we'll make it 0. If it is 0, then we'll make it 1. So, a simple procedure of changing the 1 to 0 and 0 to 1 has been implemented. And just as we had defined the probability of crossover, exactly in the same manner, we can define the probability of mutation like this. And that is going to decide that, for example, if PM is 0.02, then only 2% of the chromosomes of the population are going to participate in the mutation operator. Exactly in the same manner, we can define the procedure for mutation just as we had done for the procedure for the crossover. Again, the same example that we took last time for the crossover. Now, what we find is these are this is the population after crossover. This is what we got after crossover and their corresponding fitness. We need to generate a random number and see whether if we use probability of mutation equal to 0.2, then here it is 0.2. So you can take 0.2 and 0.2. I mean, you can take it less or less than equal to whatever you like. So this one is going to participate in the mutation operator. Here, the mutation is defined in a different manner. Instead of 1 and 0, now I can reduce it by 1. So 4 is reduced to 3. I've used a different color to indicate. Similarly, 3 is reduced to 2. So you are free to define the mutation the way you like. So I've written down below, define mutation by reducing a bit or a gene by 1 units. So that's the way the mutation is defined. And accordingly, the fitness turns out to be 36 and 44. Uh, in the second example also, this I have illustrated that this is what happens. Now apply the mutation over here in just as we had done for the ones and zeros case. Next comes the repair mechanism. Now, this kind of a mechanism is required, particularly in large problems where the genetic algorithm might not get stuck at the wrong place. So, This is also called the greedy selection. How it works is, for the fittest chromosome, if the fitness of k plus 1 is strictly greater than f of k, then keep f of k plus 1 equal to f of k, else update fk plus 1, where k is the iteration number. And we can define the elitism as to copy the fittest chromosome into the next generation as it is. And suppose the elitism size is 3, then it means that the best 3 chromosomes will be copied onto the next generation without any changes. Now this is required because uh, we want to give priority to the best individual, to the best chromosome. So without any operation, 1 or 2 or 3, whatever the elitism size has been defined, those chromosomes are going to be passed on to the next generation. So again, here is an example to illustrate that if you have this kind of a two variable problem, okay, I want you to use 5-bit strings to solve the problem using the binary genetic algorithms. So define the mapping rule, apply the tournament selection, apply the single point crossover, the single point mutation, and identify which chromosome is the best, fill in the values in the table, symbols, they are having their usual meaning. And that's how I want you to do this small bit of exercise. Okay, so that's the table I have. And in fact, I have actually given you the solution as well. All right. So in general, what I can say is that there are numerous parameters based on which the performance of a genetic algorithm may vary. And that is the flexibility that is provided in genetic algorithms. That is, you can define the crossover probability the way you like. Similarly, the mutation probability you can define the way you like, length of the chromosome, and the population size. All these are parameters which can be fine tuned to get the results to your satisfaction. Although there are many theories which tells us that the crossover probability should be between zero point 0.8 and 1, and similarly the mutation probability should be between 0 and 0.01. Similarly, the length of the chromosome will depend upon the desired accuracy, and similarly, population size is also a parameter which usually is related to the number of decision variables of the problem. So that these are some examples. I think I can illustrate this, that this is a problem which is a n variable problem. For n is equal to 2, if you put n is equal to 2, that is the number of decision parameters is 2, then this is the way the objective function looks like. The minima, in fact, the global minima is at the origin. Initially, this is a randomly generated feasible solutions, and these feasible solutions are updated over and over again like this. And finally, when the objective function uh, is converging, then this is the final solution. This information can be recorded in the form of a convergence graph, which tells us that if you represent the iterations on the horizontal axis and the objective function or the fitness, here in this case it's the objective function, the objective function is represented on the vertical axis, then the behavior can be observed like this, and it shows that initially, if the objective function is high, as in how the iterations proceed, we keep on getting better and better objective function. Yeah, so another exercise, there are so many exercises. I can pass on this PPT for you guys, and you can just look at it. So finally, I can just illustrate some of the real problems. Maybe I can do it next time because now we are just about to reach the end time. So before I close, I would like to ask you any questions that you might have. So is there any questions anybody would like to ask? Anybody, any questions?
Hello, ma'am.
Hello?
This is Dr. Nanda, ma'am.
Yes.
Uh-huh. Ma'am, actually, if you stops here, the thing, then
Okay.
we
Okay.
will take the thing from the chat box.
All
Here,
right. Okay.
people will write their comments in the chat box, and
Okay.
from the chat box, we can
Hmm.
answer.
Yeah. So I see so many questions there.
Uh,
Uh, from where do I start?
no, ma'am, just recently, if the people will put, that will answer.
Okay. So any questions you can type in the chat box, please.
Yes.
Yes. There's a question from Ayushi. Yes. Yes, Ayushi.
Ma'am, here the participants cannot unmute and do the thing. Just the chart they are typing, we have to answer.
Okay.
Mm.
Okay. Yeah. So what? That is. What are memetic algorithms? Somebody is asking.
Yes, ma'am. Memory
Sakshi.
card.
Yeah. What are memetic algorithms and how do they differ from the traditional GS? Okay, that's a very interesting question. Usually, memetic algorithms are specialized kind of genetic algorithms, and they are if you incorporate some kind of a local search in a genetic algorithm, then it's called as a memetic algorithm. That local search may be incorporated at numerous places. For example, it could be incorporated at the initial population. That is, when you generate an initial population, you could improve each of the chromosomes in the population by incorporating local search. Another way is that after applying the, let's say, the crossover or the mutation, you decide to incorporate some kind of a local search in the resulting crossover operators, and similarly the resulting mutation operators, and you can fine tune and play the way you like, so that the improvement is performed in some of the chromosomes of the genetic algorithms. So that is what are called as memetic algorithms. Yeah. Okay. So every procedure, crossover mutation, depend upon random numbers. Whether it can be harmful as fitter functions can be associated with random numbers that cannot pass through fitness functions. I I really don't understand what you are
Um,
trying to ask. Ayushi, what I want to first of all tell you is that random numbers play a very important role in all nature-inspired optimization techniques, because um, uh, these are stochastic techniques, and if you have a powerful random number generator, then that random number generator is likely to give you more and more diversity in the population. So people try to use different kinds of random numbers, and people have written theses and books on the way in which how you can generate random numbers. In fact, I have a entire lecture on how to generate random numbers using MATLAB, Python, etc. But the idea is that the random numbers should have a large period. That is, um, when you're generating random numbers on the computer, they are actually not random. They are pseudo-random numbers, because they depend upon the seed that you use for starting the sequence of random numbers. And that is how you know the performance of genetic algorithm will depend if you choose different random numbers. And in fact, when you are implementing a real life problem, particularly a large size problem, you are likely to get not exactly the same result if you execute a genetic algorithm numerous times. Therefore, what people do is, let you perform, let us say, 30 runs of a genetic algorithm, and observe their solutions. So you get 30 solutions, and from those 30 solutions, apply the statistical tests, they will Coxon's test and so on, to identify what is the behavior of the genetic algorithm for your real life problem at hand. Okay, so like this it happens. Okay, so one question: with the GA in local search, what are the algorithms can be used in global search? Uh, uh, is it possible to other nature inspired algorithms for global search and variables can be defined in global? And yeah, that's a very good question. In fact, um, initially, memetic algorithms were defined only for the genetic algorithms, but later on what people did is they experimented with other nature inspired techniques also, particularly PSO and artificial bee colony and so on. So today many people are designing memetic algorithms using the other nature inspired techniques, so there is no restriction on that, in fact, although initially it did start with genetic algorithms. Okay, so what are the limitations of GAs as compared with the other meta heuristics algorithms? Well, in fact, I would say that genetic algorithms are the most powerful kind of nature inspired techniques, because they are very versatile, because they can be implemented on real life problems, in the sense if the nature of the problem is binary, if the nature of the problem is uh, real, or tree encoding, or permutation encoding. So in fact I find that genetic algorithms do not have that many limitations as compared to PSO and others. And that's why one of genetic algorithms are my favorite ones. And I usually, sort of uh, favor genetic algorithms over the others. Of course, that doesn't mean that the others are not good, but they are very versatile. And you can use the various parameters to fine tune and get satisfactory results. Okay, yeah. So one more question. Uh, Mukesh says, can we apply GA for multi-objective large scale? Oh yes, of course you can. Actually, that's another advantage of genetic algorithms, because the the genetic algorithms are particularly suited for multi-objective. I didn't mention it in the lecture, but I want to tell you that there is a whole lot of a theory uh, based on which it is said that GAs are the most appropriate for solving multi-objective optimization problems. In fact, I would like to mention the research work of Professor Kalyanmai Deb from IIT Kanpur. Right now, he is in US. Um, he has done pioneering work on multi-objective genetic algorithms, and in fact, he has introduced a algorithm called NSGA, which is actually which is actually a specialized kind of an algorithm uh, based on genetic algorithms for solving multi-objective. And there are today improvements over the original NSGA algorithms. All right. Then there is one more question: how global and local variables can be defined? What do you mean by defined? What do you mean by? I didn't get your question, Vanitha. Yeah. What do you mean by saying global and local variables can be defined? Well, what do you mean by defining? See, defining will depend upon the problem at hand. If your problem wants that you should have um, a number of variables, you define them. All of them are global variables, all of them are global variables. The concept of global variables will stand when you are trying to do any programming. So in fact, all the variables are global. Okay, so please explain the concept of genetic drift in GAs, and also what is the role of hypermutation in GA. Okay, it looks like that's Sakshi. So Sakshi, it looks like that you have really worked on genetic algorithms. That's why you're asking this question. The concept of genetic drift tells us that for different seeds of random numbers, your genetic algorithm might uh, be drifted to a particular solution. Similarly, if you use another seed, then you are likely to drift towards another minima. And Therefore, it appears that your problem is highly complicated and highly nonlinear in nature, and therefore you need to fine tune your parameters of your genetic algorithm in a much better manner. In the sense, I would suggest you play around with the probability of crossover, probability of mutation, and the kind of crossover and the kind of mutation that you are using in your problem. Also, you might like to fine tune the population size. Once you do some kind of a simulation in that, you are likely to get better results. And of course, the sky is the limit. You can think uh, you can even think of hybridizing your genetic algorithm with any other algorithm. For example, you can hybridize your genetic algorithm with a PSO, or with a ant colony optimization, or with a ABC. So there are many ways in taking care of this genetic drift. I hope I've answered your question. Okay. So thank you so much. I'm happy that so many questions are being asked. It really tells me that people have not been sleeping in my lecture. I am so happy.
Thank you, ma'am. I just want to tell you that right now more than 210 participants are attending the thing.
That's really wonderful.
Many people
I
are
want to
there.
I want to
Just
mention
watching.
that getting getting into touch with you all guys is really very very happy for me. And in fact, this is not the end. I think this is the beginning. And you are all
Yes.
welcome
Hmm.
to contact me. My email, etc., is all there, public. It's in the public domain, so not to worry. You are free to contact me the way you like.
Yes.
Thank
And
you so
ma'am,
much.
tomorrow we will be like to listen more from you in the same
Yes,
time.
yes, yes, yes. Tomorrow
Yes.
same time I'll be
Tomorrow
joining,
same time.
and
Yes.
I'll be trying to focus on some of the applications what we have studied today.
Yes. Yes.
So thank you very much
Thank
for
you, ma'am. Thank you. Namaste.
thank you, and thank you, Professor Nanda. Thank you.